Welcome to The Explainer. Today, we're diving into a full-blown physics mystery, one that literally happens every single time you move in a circle. It's a fundamental concept for sure, governing everything from how you drive your car to how planets orbit the sun. But here's the crazy part. What you think is happening when you spin? Well, it's actually a matter of intense debate, and it depends entirely on where you happen to be standing at the time. Let's get into it.
So I want you to really think about this for a second. You know that feeling when you're at an amusement park, right? You get on one of those giant spinning cylinder rides, like the Gravitron, and suddenly you are completely pinned to the wall? Or maybe you're just sitting in the passenger seat of a car. The driver takes a left turn way too fast, and bam, you feel your entire body violently squished against the car door. Keep that incredibly visceral, real-world sensation in your head as we go through this explainer. Because, your brain is telling you, without a shadow of a doubt, that some invisible hand is pushing you outward.
But what if I told you your brain is completely lying to you? It's wild, but as Reddit user Escape77 perfectly sums up the big twist we're exploring today, what is happening is the car is changing direction and that door is slamming into you. Yeah, you heard that right. While you feel with every fiber of your being that you're being pushed out, the reality of the physics is that the door is actually pushing in on you. Okay, let's dive into this with Section 1, Centripetal, the center seeker. Time to introduce the real hero of our story.
So the word centripetal actually comes from the Latin word centrum, meaning center, and pedere, meaning to seek. Put them together and you literally get center seeking. Coined by none other than Sir Isaac Newton, centripetal force is that real inward pull that's required to keep an object moving in a curved path. Because remember Newton's laws? An object moving in a straight line wants to just keep moving in that straight line forever unless something forces it not to. That straight line tendency is just your inertia. So to force you into a circle, something has to constantly pull you toward the center.
Now, what's super interesting here is that centripetal isn't some brand new, mysterious type of force you've never heard of. It's actually more like a job title. It's a role fulfilled by everyday forces you already know all about. Like, if you swing a rock on a string, the tension of that string is playing the role of the centripetal force. When a car takes a sharp turn, the friction between the tires and the road, that's the centripetal force. And for the moon orbiting the Earth, well, gravity is stepping up to provide that center-seeking pull. If any of those forces suddenly vanished, like say the string snapped, or your car hit a patch of perfectly frictionless ice, the object would just immediately fly off in a straight tangent line.
In physics, this whole concept is mapped out with a beautifully simple formula. Centripetal force equals mass times velocity squared divided by the radius. And this formula tells a really logical story. If an object is heavier, or if it's moving faster, or if it's trying to make a much tighter turn with a smaller radius, it is going to require a lot more inward pull to keep it on that circular path. Also, notice that velocity is squared there. That means even a tiny increase in speed requires a massive increase in centripetal force just to keep you from flying out of the curve.
Moving right along to Section 2, Centrifugal, the fictitious fleeing. So if centripetal force is constantly pulling us inward, what in the world is that outward push we feel in the car? Well, this brings us to centrifugal force. This term was actually coined even earlier, way back in 1659 by the brilliant Dutch physicist Christian Huygens while he was studying the pendulums of clocks. Again, derived from Latin, centri means center and fugus means fleeing, so center fleeing. But notice a really crucial word here, apparent. In the strict rules of classical mechanics, centrifugal force is technically classified as a fictitious force.
Okay, pause right there, because this is absolutely crucial. Fictitious absolutely does not mean fake or imaginary or that you aren't actually feeling it. Not at all. It's a highly technical term. It just means the force you're feeling isn't coming from some external object physically pushing you. It is actually just your own mass, your own momentum, desperately wanting to continue traveling in a straight line while your environment curves around you. The force is a physical manifestation of your own momentum resisting a change in direction.
To make this crystal clear, let's look at this remarkably vivid analogy from Reddit user AP1MSC. They said, centripetal force is the superhero swinging the villain over their head by the rope. They need to pull on that rope very hard to keep the villain from flying off. Centripetal motion is what you experience as the villain. Think about it. If you're standing on the ground watching this happen, you clearly see the superhero pulling inward. But if you are the spinning villain, you feel like an invisible monster is trying to fling you out into space. The rope isn't pushing you out, it's just constraining your natural urge to fly straight.
And here's another beautiful way to visualize it, this one from user TheGnome54. Imagine spinning a flower around super fast.
The petals want to fly off, but they're held to the core by the centripetal force. To the core, the petals are fleeing, which is centrifugal. The outward push is simply the petal's natural inertia being constrained by the stem. It's like a giant puzzle, and it all fits together perfectly.
Which brings us to Section 3. Frame of reference changes everything. We've arrived at the absolute climax of our explainer, folks. The entire phenomenon, the whole reason these two terms exist and confuse physics students every single year, hinges entirely on one thing: where the observer is standing. And this brilliantly illustrates the concept of frames of reference. If you're standing still on the sidewalk, what physicists call an inertial frame, and you watch a car take a sharp turn, you see the car's tires creating an inward centripetal force, and you literally see the car door intercept the passenger's straight-line path. But if you're inside that turning car, in a rotating frame of reference, you don't perceive your own forward momentum. You just feel yourself being violently shoved outward against the door. Both forces are describing the exact same event, just experienced from two completely different viewpoints.
Now, because they sound so similar, a massive misconception is that these two forces just cancel each other out, kind of like an action-reaction pair from Newton's third law. But actually they don't. To be an action-reaction pair, forces must exist in the exact same reference frame and act on two different interacting bodies. Centripetal is a real physical force in a stationary frame. Centrifugal is an apparent force of inertia in a spinning frame. You literally cannot apply them both at the same time to the same observer.
Let's move to Section 4, Real-World Spinning Applications, and see how this builds into some seriously cool technology.
Because while centrifugal force might technically be called fictitious, the effects are incredibly real and useful. Within a rotating frame, this apparent force acts like a ridiculously powerful tool. Take laboratory centrifuges, for example. By spinning fluid-filled tubes, we create a hydrostatic pressure gradient. According to our sources, some commercial ultracentrifuges spin so incredibly fast they generate 2 million Gs of acceleration. No way, right? 2 million! This forces denser particles outward, acting essentially like a supercharged version of Archimedes' principle, a buoyancy. We use this exact same principle for centrifugal governors inside engines, casting molds with liquid metal, and yes, pinning thrill seekers to the walls of the gravitron ride in apparent defiance of Earth's gravity.
But perhaps the most sci-fi application of all is creating artificial gravity in space. By designing a space station as a massive rotating ring, the astronauts inside become the villain on the superhero's rope, or the water in the spinning bucket. Their own inertia, their centrifugal force, pushes them against the outer hull of the station. If you spin it at exactly the right speed, that outward push perfectly simulates the 1G pull of Earth's gravity, which actually allows astronauts to walk on the walls. How cool is that? It's amazing to look back and see how our understanding of these rotating frames has evolved so dramatically over the centuries. In 1659, Christian Huygens was basically just trying to build better pendulum clocks when he coined the term centrifugal. A few decades later, in 1687, Isaac Newton mathematically defined the real, center-seeking centripetal force to explain how planets orbit the sun. But it wasn't until 1914 that Albert Einstein took these rotating reference frames and linked them to the equivalence principle in his theory of general relativity, showing us just how deep the rabbit hole of apparent forces really goes.
Which brings us to one final, truly fascinating thought. The Earth you are sitting on right this very second is a rotating frame of reference. We are spinning at roughly 1,000 miles per hour at the equator. So does that mean you are currently experiencing a centrifugal force pushing you out into space? And if so, does that tiny outward push actually make you weigh less at the equator than you do at the North Pole? I'll leave you to ponder how your own frame of reference affects the forces you feel every single second of your life. Thanks for joining me on this explainer, and keep questioning your perspective.